Hi! Can you believe the week is almost over and another DAC will be coming to a close? I'm a bit sad, but I know there's another show next year. We hope you've enjoyed the virtual conference so far. 5G and I have had a wonderful time being your guide during this virtual event. Right, 5G? The exhibits are now closed for live interaction, but their content and contacts are still available for you to view and set up meetings. The research, designer, IP, and embedded tracks continue today with new sessions that will start at 1 p.m. If you did not get a chance to attend the late-breaking results and work-in-progress poster session this morning, I suggest you take a look. This will give you an opportunity to see what our innovative engineers are working on currently. Today we will host our last session of the happy hours. It has been a fun week catching up and sharing stories with these live happy hours. Share your week's experience with Zwa, our general chair. Or do you have a pet that shares your home office with you? Or maybe a pet that you just enjoy spending time with? Stop in and show off your pets. There are still sessions to attend tomorrow, Friday, so make sure you look at the agenda along with award ceremonies. At this time, we would like to once again thank our industry sponsors. Without their support, DAC would not be the greatest show for the electronic design ecosystem and the design automation community. But most of all, we want to thank and recognize our conference sponsors, ACM SIGDA and IEEE CETA. This will be my last day at DAC 2020, but I look forward to seeing all of you in 2021. Here is Zwa Lee, the 57th DAC chair, to kick off Thursday.
Thank you, Debbie. Welcome to DAC Thursday. As Debbie DAC just highlighted, we prepared another day packed with exciting program for you. Please also do remember that we have a full day program on Friday at this year's DAC as well. Also, we're going to announce the DAC Best Paper Award and the Best Design IP Embedded Track Presentation Award winner tomorrow afternoon. Today, I traveled to Tokyo, Japan, standing in front of the Olympic Stadium. As you all know, due to COVID-19 pandemic, the Tokyo Olympic rescheduled to 2021. I recently found out that many new technologies actually showcased at Olympic Games in the past. For example, 1964 Tokyo Olympics. That's the first time the opening ceremony was televised from Japan to the United States and the rest of the world through satellite, so that the international audience can watch the opening ceremony on the TV without waiting for tapes. And that year Olympic, later also known as TV Olympics. I read the news that 5G could play a big role for 2021 Tokyo Olympics. Combined with technologies such as VR and hologram, 5G could completely change the way how we watch and interact for the sport games. Maybe after next year, people may call the 2021 Tokyo Olympic as 5G Olympic. 5G has made lots of new opportunities and moved the Internet of Things to the next level. Combined with other technology advancements such as more energy efficient chips, edge computing, machine learning, and AI, it could create many other new things that we could not imagine today. And while we're talking about 5G now, someone out there already looking for the next wave of communication technology. Today, it is my great pleasure to introduce Dr. Andrea Goldsmith from Stanford University. And she will talk about the new paradigm of a 6G wireless communication. This is Andrea's first DAC. It is amazing to see such idea sharing across different industries and communities. You know, we have the chip and EDA community, machine learning and AI community, now wireless communication community, security community, and autonomous system community. Imagine we all work together, through with the barriers and collaboration, idea sharing, then we can contribute to the human society in a much bigger way as a bigger community together. Dr. Andrea Goldsmith is a Stephen Harris Professor of the School of Engineering and a Professor of Electrical Engineering at Stanford University. She co-founded and served as CTO of the Plume Wireless and of Quantenna Incorporation. She also served as the board of directors of Crown Castle and Medtronic. She has had different industry positions at Maximum Technologies, MaryLink Corporation, and AT&T Bell. Dr. Goldsmith is a member of the National Academy of Engineering, American Academy of Arts and Sciences, a fellow of IEEE and of Stanford. She has received several awards for her work, including IEEE Thunder Award, ACM Athena Lecture Award, IEEE Communication Society Edwin Armstrong Achievement Award, National Academy of Engineering Gilbreth Lecture Award, the Women of Wireless Communication Technology Mentor Award, and then the Silicon Valley San Jose Business of Journal Women of Influence Award. Her research interest is in information theory and communication theory and their applications to the wireless communication and related field. She is the author of the book Wireless Communication and co-author of 2 other books and inventor of 29 patents. She received the bachelor, master, and PhD degree all from UC Berkeley. Before Andrea starts, I would like to thank all of you again to attend DAC 2020, the first virtual DAC. Please keep yourself and family safe. The whole EC team and I look forward to meeting you again at DAC 2021 back in San Francisco, and hopefully face-to-face in person. Please enjoy the remaining 2 days for the rest of the program. And now, let's welcome Andrea Goldsmith.
Hello and welcome to my keynote, New Paradigms for 6G Wireless Communication. I'm delighted to be here. This is my first DAC conference. I wish I was actually here in person to speak to all of you and answer your questions, but it's an unusual time. So thank you to the organizers for inviting me, and I'm really looking forward to sharing with you my perspectives on 6G wireless communications. So I've been working in wireless communications for my entire career, since the mid-'80s when I had a job working on satellite communications in a defense startup communication company in Silicon Valley, right off 101 and Great American Parkway. It was a very different time in Silicon Valley. It was a very different time for wireless communication. This was 1986. The first cellular systems had just been launched in Chicago a few years earlier. Nobody predicted that wireless communication would become the pervasive necessity that it is today, particularly in this era of COVID when we do everything virtually. So even though I've worked in wireless communications through all of the generations of cellular and all of the generations of Wi-Fi, which were launched a few years later, I actually believe that this is the most exciting time for wireless communication. And the reason is that we're transitioning from a paradigm where our earlier generations of wireless were really about people talking to each other, first on cell phones, analog cell phones, and then digital cell phones, and then we transitioned to short messaging and data at low data rates and then at higher data rates. We used wireless communication to download information from the internet. What's changing now and what's really exciting about 5G and future generations of cellular and Wi-Fi is that we're really moving to a new paradigm where many, many more devices are going to be using wireless networks for connectivity. And so we're moving into an era where communication is not just people either talking to each other or accessing information, but there's much more device-to-device communication. And that's going to enable applications such as pervasive sensing, such as autonomous vehicles, in-body communication between our biomedical devices, sensing on our bodies, smart cities where basically you don't need to have the garbage collector come by every Wednesday, but in fact, they'll come by when the garbage can is full because the garbage can calls the trash collector. If you have an elderly person in an assisted living situation, you can use this smart sensing to determine when they fall and call an ambulance. That's part of the smart city and smart building paradigm. So there's many, many exciting applications on the horizon for this next generation of wireless communication. But there's many challenges as well, and that's what makes it such an exciting time to be doing research in wireless communication. One of the biggest challenges is the fact that the licensed airwaves are basically full. So these are the parts of the spectral band that are licensed to the cellular operators to use for their cellular communication. And this chart, it's an older chart from the FCC, which basically predicted that given the exponential growth in demand for data, and this was projected out to 2014, we would be in spectrum deficit of about 300 megahertz by 2014, which means that we just wouldn't have enough spectrum in the license bands to support all the demands for data starting in 2013, so starting 7 years ago. Obviously, the demand for wireless data has only grown since this prediction was made. So you might ask, well, why is it that our devices can connect at all to the internet and download data? And the reason is because we're not using the license band primarily for downloading massive amounts of data. We're in fact using Wi-Fi. And the Wi-Fi spectrum has in fact 300 megahertz of spectrum in the 5 gigahertz band. It's got 80 megahertz of spectrum in the 2.4 gigahertz band. And so the reason that this dire situation that was predicted by the FCC saying we didn't have enough spectrum to support wireless data didn't come to pass is that was only about licensed spectrum, whereas we also use the unlicensed band. Now, one of the things that's very exciting about 5G and beyond is the fact that we're actually going up to much higher frequencies. We're going to the millimeter wave band, where there's tens of gigahertz of spectrum in the millimeter wave and terahertz bands. But those are very challenging bands to use due to the laws of physics associated with sending signals at those very high frequencies. And I'll touch on that a little bit more later on. Another area that I've done research in, which is a lot of fun, is molecular communication. So we don't necessarily need to use electromagnetic waves to send signals. We can actually use molecules and embed data, ones and zeros, into molecules. And we've actually done some research in molecular communication. And this would be very useful for in-body types of communication, where you're trying to send a signal to a drug delivery system or to an artificial heart or an artificial device, a lung inside your body, to make it do something different or to adjust the way that it's operating. So I'm not going to talk about molecular communication because it's not really part of 5G communication, but it is a very exciting area of research in communications, if not wireless. So the FCC predicted back in 2010 that we'd be in spectrum deficit, and we are in the license band. But we have a whole new paradigm of wireless communication that's on the horizon, and that is what's referred to as the Internet of Things. So the idea of the Internet of Things is that basically any device with an on-off switch will be able to connect to each other into the backbone Internet. And the growth of the Internet of Things is predicted to increase the number of devices using the wireless spectrum by billions. So we will have billions of devices operating in the same wireless spectrum that we use today. And so this is going to increase the demand for wireless spectrum even more. So we need to find ways to support these new devices. One of the other interesting paradigms of the Internet of Things is that the requirements of these devices are very different than the requirements of our smartphones. So our smartphones have generally asked us to consume more data, to have faster connections, to extend the battery life of the smartphones, whereas many of these Internet of Things devices are actually low data rates. So if you think about pervasive sensing or smart sensing that's in my clothing or inside my body or on my tennis shoes, these are low data rates where I'm collecting small amounts of data, But the energy consumption of these devices is also very constrained because often they need to operate on very small batteries, not the kind of battery that we have in a smartphone. So if that's the case, we need to build a network, a wireless network, that can support not only our smartphones, which are going faster and consuming more data and doing more and more high-rate applications, but also these small Internet of Things devices, which have low data rates but extreme power constraints. So one of the challenges for us wireless network designers is how are we going to build one network that can support such a heterogeneous set of devices. Now, I've talked a little bit about the Internet of Things, but I haven't really told you what it is. So I'd like to define, what is it that this billions of new devices are going to be in terms of the Internet of Things. So basically, the Internet of Things, according to me, my definition is that every electronic device, everything with an on-off switch, will be able to connect to every other electronic device as well as to the backbone Internet. Now, of course, we already have devices like that. Our smartphones connect to the Internet. Many consumer electronics, you have refrigerators that connect to the Internet. My car connects to the Internet. We have things like Nest temperature sensors, doorbells that connect to the Internet. There are medical devices that connect to the Internet. So there's many, many devices now. The vision for the Internet of Things is that not only those devices, but basically every device with an on-off switch will connect to every other device into the Internet. Now, that's not so interesting if you just think about the fact that my shoes can talk to your shoes and they can have a nice conversation. There's not a lot of value in that conversation. The value in the Internet of Things, in all these devices having the capability to talk to each other and to the backbone, is in the data processing. It's what data can we extract from these devices and how do we use that data to do intelligent things like autonomy or to sense when there's a danger of a bridge collapsing or a danger of an earthquake and get that information very quickly into the cloud, out to the emergency responders and so forth. And that data may not necessarily go all the way to the cloud. It may sit at the edge. So this is something that's very important for autonomy or for augmented reality, where you can't have the latency associated with sending all the data to the cloud. So then you're going to have processing at the edge of the network that can respond much more quickly to the data that it receives to process that data and extract the useful information. So there's many different verticals that the Internet of Things can apply to, many different places where the Internet of Things may end up being a very powerful paradigm and make people lots of money. If you ask me, what is the killer application for the Internet of Things, I would probably say, well, if I knew, I wouldn't tell you. I'd go do a startup around it. But the truth is, I don't know, and none of us know. I don't believe anybody knows which paradigm of the Internet of Things is going to be the most successful. And, the Internet of Things is also a little bit of a buzzword. There's a lot of hype around it. But the reason I think that there's reality, tangible benefit, and value to be extracted from the Internet of Things is that there's companies and technologies that are already making money on this paradigm in all of the different sectors that I show here. So in the transportation sector, in security, in smart infrastructure, healthcare, industrial automation, all of these are segments that are using devices that are extracting information, sending that information to a processing center, either at the edge or behind a firewall or in the cloud, and using that information in a way that extracts value. So I don't know if any of these applications shown here are going to be the biggest application for the Internet of Things. Maybe all of them will go by the wayside. Maybe some of them will be successful and some won't. But at the end of the day, it's very clear that there is value to be extracted and money to be made from the Internet of Things. Okay, so when I look at the promise of 5G and I say, okay, what is it that we're going to be able to do with 5G networks that we're not able to do with today's networks? And it's really that every generation of cellular and Wi-Fi up until now has really been about just one of the three edges of this triangle. It's been getting higher data rates. And the promise of 5G was that not only would we get an order of magnitude higher data rates than we have today, but we would also be able to support on the same network devices that had very low energy, very severe energy constraints, so that, for example, they could last for 10 years on one battery. Wouldn't it be nice if our cell phones could do that? But of course, if you're embedding a sensor in a shoe or in a tennis racket or in a bridge, you want it to last as long as possible. So one of the new paradigms for 5G networks was that in addition to getting higher than 10 gigabit per second data rates, which we get today on Wi-Fi, but not on cellular. We're 1 to 2 orders of magnitude away from that with cellular. In addition to that very high data rate, we can also have devices on this network that can last a long time on very low energy, maybe even collecting energy from the environment around that. And then the other angle or the other corner of this triangle is very, very high reliability, so that you have very low latency and very high reliability for doing things like automation. So if I have a network of cars that are using this backbone internet, wireless internet, to talk to each other and avoid crashing into each other, I need very low latency and I need that network to be reliable. And these parts of the triangle where we're getting much higher data rates and when we're getting much higher battery use and much higher reliability are things that we actually haven't done before. So these are things that we haven't previously done with our networks up until this generation. Okay, so how are we going to actually go about building networks like that? How are we going to build networks that can support these very high data rates, very low latency, and very high reliability? Well, this is where the fun comes in if you're a wireless network designer, because there's many interesting paradigms to pursue in terms of supporting those requirements of the network. So one thing that I do a lot of work on is completely rethinking cellular system design. So this may come as a surprise to most people, but in fact, the basic premise of cellular system design, which is that we put these base stations in the middle of cells. So we take a city or an area, maybe a rural area, or a suburban area, or a city. We divide it up into these hexagonal cells, which are approximately circles. We put base stations in the middle of those cells, which are covering the whole cellular area. And then each of the base stations are assigned a set of channels, and they reuse the same channels to get the maximum spectral efficiency, but they reuse them such that they make the interference low enough to not cause a lot of interference to other cells. So, for example, this cell right here might be using the same frequency as the adjacent cell, and then you may use signal processing or power control or other techniques to avoid having interference between the different cells that are using the exact same frequencies. Now, that paradigm for cellular system design, where I take a city and I divide it up into these non-overlapping cells and I put a base station in the middle of each cell, that paradigm was actually developed in 1946 in a paper by D.H. Ring that appeared in Bell System Technical Journal, BSTJ. So the concept is 60 years old. And even though we've obviously evolved the technology that we use in cellular systems, I mean, those original systems were analog, now they're digital. We have many antennas, we have relaying, we have many different new technologies that we've embedded into this cellular system design, but we haven't really rethought the basic architecture. And so there's an opening to go back and say, given how technology has evolved over these many decades, maybe we should be thinking about a completely different cellular system design. And I'll talk about that a little bit more later in my talk as well. Of course, we want to use more spectrum. And as I said, there's these millimeter wave bands that we want to take advantage of so that we don't have the spectrum shortage that the FCC predicted so long ago. We want to develop very low power radios. And I think this is a place where design and design automation comes in to building radios that can last for 10 years on a single battery. Multiple antennas is an amazing paradigm to get higher data rates. And in fact, the way that these multiple antennas work is you basically point the beam in the direction of the radio that you want to talk to, and that gets around many of the challenges of millimeter wave communication, particularly the very high path loss that results. The problem with doing massive MIMO in this way is that there's propagation challenges, which I'll talk about in a second, in a couple of slides. We can also do multi-hop routing. So if we go back to the cellular system design, we can have relays that are doing multi-hop routing, particularly when you're going to a radio that has very low power, may not have sufficient power to get all the way back to the base station, but we can send a signal to a relay, which then relays it back to the base station. There's other paradigms in cellular like small cells and base station cooperation and distributed antennas, and I'll talk about all of these a little bit later. But these are all techniques that we've incorporated into cellular system design. And then another thing that's really important is the notion of cloud optimization for some of the network resource allocation and optimization. But if you have to send everything back to the cloud to do the optimization is too complex and there's a lot of latency. So we also want to look at fog optimization. So I'll be talking about all these things shortly. The last bullet item here is machine learning. So, of course, I know there's a whole session on machine learning, another keynote. And you could say, well, why do we need to do any of these designs? Any of the things pictured here, why don't we just let machine learning solve everything in air design? Can't it enable everything? And so it turns out that I've actually done some work in machine learning. It can enable everything, but it does actually have a role to play in this next generation of cellular systems. So let me talk about that a little bit. So the main focus that I've had in using machine learning is in physical layer design, where we're trying to design the radio to say, okay, I have some bits coming in. I need to send them over a channel, which is an analog channel, and hopefully recreate exactly the same bits at the receiver that receives the signal from the channel. And if you look at this picture on this slide, if you open any book on communication systems, you'll have the exact same picture. So this is the basic block diagram of a communication system where you have a message, which may be an analog signal like a voice signal or a radio signal from your FM radio station. It goes to a transmitter, which sends the message over the analog channel. The message may also be bits, and then the transmitter needs to convert the bits into an analog signal to send over the channel. There's noise, maybe interference introduced. You go through an A to D converter, do digital signal processing at the receiver to recreate the message that was sent, whether it's bits or an analog signal. So this is the traditional block diagram for a physical layer and communication system. The problem is that this assumes that the channel, H of F, the analog channel, this is the frequency response of that channel, it assumes that's known. In order to design my transmitter and receiver, or at least to design my receiver to compensate for the distortion that's introduced by the analog channel, I need to know the channel. So that's one problem, because the accurate channel models may not be known. In fact, when we did our work in molecular communication, you're not using electromagnetic waves, you're using a diffusion process, and there is no good mathematical model for the channel that you're sending those molecular signals over. That's also true in millimeter wave and terahertz radio channels, because we don't have good channel models at those high frequencies. Even when you know the channel perfectly, so even if I know H of F, it may be that that channel is so complex in terms of the distortion that it introduces that the optimal algorithm to compensate for that distortion, the Viterbi algorithm, for example, may be not computationally efficient. It may not be feasible with one of these small devices that's running on a 10-year battery. So the two issues that machine learning can actually solve in the paradigm of physical layer design is I don't need to know the channel H of F. I can learn it from the data. And I can use a receiver that's lower complexity than the optimal one, because machine learning, after you've done the training and learned the channel model, it's actually a lot simpler than a traditional Viterbi algorithm, for example, that has a lot of distortion to compensate for. And the solution is robust estimation error, because the machine learning approach doesn't try to invert the channel. It doesn't assume that it knows the channel. It's just learning from the data. And this is just an example of intersymbol interference channel, where if you knew the channel perfectly, the Viterbi algorithm is optimal and it has the lowest error rate. But you see the green with the dashed lines is the Viterbi algorithm that doesn't know the channel perfectly. There's some estimation error. And you see that the machine learning approach in red can actually do better than the optimal Viterbi algorithm when the channel isn't perfectly known. And we have other work that shows that, in fact, if there's a complexity constraint on the Viterbi algorithm, then the machine learning also does better than Viterbi, which is optimal in the absence of complexity constraints and knowing the channel perfectly. So ML is a bandwagon. I don't usually like to do research in areas that everybody's jumping onto. And I tried to avoid machine learning altogether, but when we started this work in molecular communication, there was no other option because we didn't have a channel model. And what we found was that we could actually beat all of the existing approaches to doing compensation for intersymbol interference on this molecular channel. So that got us interested in looking at machine learning more broadly. And so rather than running away screaming because everybody was working on machine learning, we actually came to realize that our domain knowledge of designing communication systems and our algorithms for machine learning, which were we actually developed some new machine learning algorithms based on traditional signal processing approaches applied to these channels with distortion. So we actually advanced the state of the art in machine learning as well as in channel equalization by developing these machine learning algorithms. So basically, I believe that machine learning has a role to play in wireless system design. I know for sure it has a role to play in the physical layer design because we've already applied it both to this equalization problem, which we were able to beat the optimal Viterbi algorithm when the Viterbi algorithm didn't have perfect channel knowledge or was complexity constrained. We've also been applying it recently to encoders and decoders of polar codes and also LVPC codes. So there's very interesting role for machine learning to play at the physical layer. Now, as I go up in this networking stack, network resource allocation has always been a very hard problem. It's an NP complete problem just for channel allocation. So maybe there's a role for machine learning to play there, but we haven't determined that yet. ML may also teach us how to do distributed learning. So if you look at these distributed sensor systems where you have pervasive sensing, perhaps rather than applying traditional algorithms, we can apply machine learning. And also, it may provide some breakthrough to cross-layer design when we're trying to design these wireless networks to support a particular application like HR, virtual reality or augmented reality or low resolution video or voice or something like that. And we've actually done some work on using machine learning for joint compression and channel coding and showed that it actually did better than traditional techniques. Okay, I want to talk a little bit about millimeter wave. Again, the millimeter wave band is up in the 60 to 100 gigahertz range, roughly, and there's tens of gigahertz of spectrum up there. So basically, every wireless system, commercial system in use today, can fit into the spectrum of the millimeter wave band. So massive amount of spectrum. We really want to be able to take advantage of that spectrum. The problem is that millimeter wave transmission has very large attenuation and path loss because the path loss is proportional to 1 over frequency squared. So at these very high frequencies, the signal power falls off very, very quickly. Now, one way around that is to use something called massive MIMO, where we have these hundreds of antennas. And through those hundreds of antennas, we're able to, as I mentioned earlier, point a beam directly in the at the receiver that we want to talk to. And it turns out that doing that allows me to avoid a lot of this very high attenuation. The problem is twofold. One is that in order to be able to point the beam directly at the receiver that I want to talk to, I need to know the channel in that direction. And if I have hundreds of antenna elements at this massive MIMO array, that's hundreds of antenna parameters, channel gains, that I need to know. So there's a lot of overhead in learning the channel gains that would allow me to point the beam. And the other problem is that if something gets in the way of the beam, if something blocks it, I no longer have this very nice, beautiful pencil beam to my receiver, but the signal scatters in all directions. So there's many challenges to trying to build in practice these millimeter wave massive MIMO systems. And you will likely need multi-hop, because all of the data that I've seen in terms of the field trials for millimeter wave, even with massive MIMO, the distances that these signals can travel in practice in practical environments is not very far, which means that we're going to have multi-hop in order to extend the range of millimeter wave. It's not going to be possible to do point-to-point millimeter wave beyond, a few tens of meters from that massive MIMO antenna unless you also include multi-hop communication, which has challenges of its own. Okay, I talked a little bit about rethinking cellular system design. As I mentioned, the traditional design, the one that was done by D.H. Ring in the 1940s, assumed that the system is interference limited. So you're basically reusing frequencies such that the interference that you cause to another cell that's using the same frequency as you are is tolerable for the type of application that you want to do. The Shannon capacity of a cellular system is unknown unless you assume that there's this big cloud ran in the sky that is treating all the base stations as just distributed antennas, so it looks like one big distributed antenna, and then we know the capacity. But that's not practical, so we basically don't know the capacity of these cellular systems, which means we can't necessarily take our designs and know how close we are to the fundamental limits of these systems. Now, this notion of designing cellular systems to be interference limited is not necessarily the case anymore, because these massive MIMO antennas allow me to point my beam in the direction of my receiver, so I'm not causing interference to other users. I can also use signal processing to do multi-user detection to subtract out the interference. I can also have these base stations that cooperate. So now I form a virtual cell through the base station cooperation. And so the receivers that I was interfering with before, if these base stations were using the same frequency, I'm no longer interfering because these base stations are cooperating. And I can also use relays as well, which changes the interference paradigm. So as soon as you start bringing in some of these techniques like cooperative base stations and relaying and small cells, it raises the question of what is a cell? And this is what I was alluding to earlier about going back to the drawing board and saying, maybe we need to completely rethink the way we do cellular system design. And when we do that, when we say, okay, how should we design these systems? Perhaps we're going to look at another metric for the design than just how do we get to faster data rates, which is how we've been designing these cellular systems up until now. So some of the questions that we might ask could be, do I care about coverage, or do I care about energy consumption in addition to data rate? So these are some of the questions that we need to ask. And we also need a way to deploy these networks and these small cells in a much more automated way. And I'll touch on that shortly. In fact, in the next slide. So small cells are the solution to increasing cellular system capacity. I've worked in small cells since my very early days as an academic at Caltech. One of my first papers as an academic in the mid-90s was on small cells in cellular systems and the fact that they lead to exponential capacity gain. And the reason is that basically if you take an area and you deploy a bunch of these macrocells, you can only support a certain number of users. If you shrink the cell size, you can support that same number of users, but now in the smaller cells. So in the overall area, you get this exponential gain in capacity. Now, you can't just deploy a network of small cells because you need to have coverage, widespread coverage, from the moment that you start operating your system. So the way these networks are typically deployed is we deploy large cells, macrocells, initially to get coverage so that you can used your phone in the new system anywhere. Then you look at the hotspots where you're limited in capacity and you deploy the small cells into those hotspots. And then eventually you keep deploying small cells until you have sufficient capacity for all your users. Now, the way that you want to deploy these small cells right now for large cells, you have people that go out and mount the antennas and drive around and set all the parameters, and then those parameters are fixed once they're done and they never go back. That's not a very efficient or effective way to do the optimization. So we'd like to have self-optimization in the cloud, where these small cells and maybe the large cells send information up to the cloud figures out how to configure the network, and then sends the information back. And that way you can reconfigure the network, you can change dynamically your resource allocation. So if at one point in time you've got a football stadium where there's a lot of people, hopefully someday we'll go back to having a lot of people in football stadiums, you can deploy a lot more resources to the large and small cells that are in or around that football stadium to support those users. And then when the game's over, you can redeploy those resources to the other cells in the network. So this requires this kind of dynamic optimization. The problem is that this is a hard problem, not just a hard problem, it's an NP hard problem. So this is something that I looked at again in the mid-90s when we were looking at cellular systems that had frequency allocation only. And then it was a graph coloring problem. It's an NP hard problem. Now the systems have evolved to have multiple antennas and power control, large and small cells. This becomes a really hard optimization problem. But fortunately, we have also advanced our optimization tools. So we have many optimization tools to solve this NP really hard problem. But the interesting thing, and this is one of the things that we've been working on recently, is that you don't necessarily want to do all the optimization in the cloud, because by the time you've sent all that information up to the cloud, the network may have changed. Moreover, that NP really hard problem, if you're doing it all in the cloud, the complexity is very, very high. So one of the things that we've been looking at is forming neighborhoods of base stations. We call this fog optimization, where we say, okay, rather than optimize the entire network and all the base stations together, we'll form clusters. These clusters have minimal interference to each other, so we do fog optimization of the network resources. Obviously, that's suboptimal to cloud optimization, assuming no latency and sending the data to the cloud and no complexity constraints. But in practice, we will have those constraints, and fog optimization can do better. Machine learning can also play a role here. I alluded to this when I talked about machine learning, but we haven't actually yet determined how to formulate the problem in a way that machine learning can actually help. So this is a topic of future work. In addition to that, we also want to look at things like, where should we put computation? We should put some at the edge. How much should we put at the edge? How much storage should we have at the edge? So these are questions that need to be asked for this next generation of cellular that's going to have computation and caching at the edge. And this slide just shows the trade-off. It's a little bit busy with the figures, but basically it's showing the benefits of going from fully centralized to fully distributed. So we get this 10x loss if we're doing joint decoding across all the cooperating base stations. And here we have a 55% loss. Both of these are really big, going from doing all the optimization in the cloud, which is where I only have one virtual cell, to fully distributed, where every cell is on its own and doing its own optimization. And you see that basically by forming these virtual neighborhoods of, say, 2 or 3 or 4 cells, we get closer to the benefits of fully centralized optimization. And we're not paying as much of a performance price as we would if we were doing fully decentralized. So this kind of leads to the notion of cloud-enabled wireless networks more generally, not just to do optimization in the cloud for the cellular networks, but for all the different networks that we are using in terms of wireless. So this is my notion of cloud-enabled wireless networking. And this leads to the paradigm of software-defined networks. So in a software-defined network, basically you have a unified control plane, which looks at your application, say it's video or autonomous vehicles, figures out the different parameters of the different wireless networks. So Wi-Fi and cellular and millimeter wave have different optimizations of their base stations. And this unified control plane can then figure out, given the networking conditions and the way that it's allocated resources within and across these different networks, it can decide, okay, what is the best network for me to operate my video over? And typically that might be millimeter wave because millimeter wave has the most spectrum. But as the user moves away from the millimeter wave base station, it can no longer talk to it. It no longer has good connectivity. And then this unified control plane can hand over the video to the cellular system. Of course, the video may need to decrease its data rate by using a less high definition compression because now on the cellular network, it doesn't have the same data rates it had with the millimeter wave. So this is the notion of software-defined networking architecture. And in fact, if you take this one step further, you could say that there are no networks. There's no Wi-Fi, no cellular. Basically, what we have is a bunch of distributed antennas at different frequencies, and the unified control plane figures out what resources to allocate to these different antennas and how to connect up the applications to the different antennas to support their application requirements. This is really critical when we're talking about coupled networks. So, for example, with autonomous vehicles, we know that we need a network that's extremely robust and reliable. And so maybe you don't want to use millimeter wave networking because it is one of the least robust due to the propagation challenges associated with millimeter wave. If you're looking at interconnected networks like transportation and the power grid, or even if you're looking at the Internet of Things, where you're using these devices to collect data and send it to the cloud. All of these kinds of coupled networks would benefit a great deal from this software-defined networking paradigm. Same with the smart grid, where we're actually using the backbone wireless network to figure out where the energy should be going, what the energy demands are, and so forth. So just to give a quick snapshot of what is 6G and beyond 6G, at least my vision for it, is that basically all technologies combined that will allow people and organizations to interact in the digital world. So this is everything from including data science and biomedical devices and the hardware and circuits and materials that we're going to need to enable this next generation and future generations of wireless communication so that basically wireless connectivity is seamless and it's able to connect people everywhere in the world. It's able to connect devices regardless of their requirements, regardless of their constraints. This is going to require not just people working in wireless communication, but working in many areas of technology beyond just the wireless piece of it. So just to summarize, it's a very exciting time to be doing research in wireless communication. This will enable new applications, far broader sets of applications than we have today. Future wireless networks need to support higher data rates, extreme energy efficiency, as well as low latency. Some of the enablers for doing this are small cells and massive MIMO. We need a very robust physical layer, especially for these mission-critical applications like autonomy, and machine learning is a promising new tool that we're just barely scratching the surface of how we can use it in these future systems. Cloud and fog-based networking is another new paradigm. Lots of exciting work to be done to see how do we allocate our resources, how do we build these networks to have caching and computation at the edge in the cloud, and how do we use those resources most effectively? And then finally, this notion of the software-defined wireless networking is needed so that we can see how do we support these different applications given the heterogeneous requirements they have and the heterogeneous networks that we have. And with that, I'll end. Thank you very much for your attention.